Yeah, but yeah, so I just wanted to tell that we are 9 university that works with Infravis. We have Chalmers, Gothenburg, KTH, Linköping University, Lund, Linneum, Mid Sweden, Umeå University, and Uppsala University, and we are funded by Vetenskapsrådet. So basically, Infravis is people infrastructure, and we don't provide equipments or hardware. We basically work with the people, like users that wants to help in their research or their different projects. And so basically, this was initially like supported projects that were actually selected for the Infravis infrastructure. So these were like the pilot projects that was built in like in around like 2022 or something like that. So these were like also the inspiration for the for the users who can actually work with visualization domain. So we have like a couple of different topics that we could cover into this. And basically, the Chalmers is the host, and the director is Monica Billiker. And then we have strategic steering group. The chair is Anders Hast from Linköping University. And then we have node coordinators. And here in Uppsala, we have Ingela in Lindström and other additional 7 other universities that they also have node coordinators. And yeah, and then we have around 50 application experts here in Infravis. So this is like how the whole Sweden looks like in regards of like the distribution of experts. So we are around 50 people working with this infrastructure. And I think you can see Linköping has the most, and Lund University, they have the most of the attendance, like people who work with Infravis. But yeah, we also have some in Uppsala. And Gent is also partially working with Infravis, like around 10-15%. So what we offer like expertise in visualization, AI, and human in loop. Competence, we have competence from all these universities in Sweden. And tools, we integrate tools, methods, and make like also like make big tools like interactive tools for the users. And we have accessibility to the national infrastructures and the laboratories, which we have also like in Lund universities, Linköping, like, and also NAISS can also be accessible through this. And so we help in data collection and curation, machine learning and AI, statistical data analysis, data visualization, and also interactive collaborative visual analysis. So these are the flow chain that we follow. And so this is like the support, the organizations that have received supports from Infravis from 2022 until 2024. So we still have to make this for 2025, but we are waiting for this ending report. So you can see actually we just haven't given the support to the own universities and national academic universities, but we also have given support to the non-academic Swedish, like for example, Max 4, we have SLU, and we have KI, Akademiska Sjukhuset here in Uppsala, and also the international Stanford was also one guide. So this is like the distribution you can see. And here, so we have like 3 level of support. Help desk, which is, yeah, you can just ask normal questions, totally free. And mid-level support, it's free of charge. If you have project that requires just 100 hours support, that is also free. So here we just analyze and data visualization with expertise. We also have, we help in data clinic and writing funding application. And if we go for like in-depth, the contain more than 100 hours, then we apply for charge. So I think it's per hour around something to 40 or something krona. But then we also have yearly I think every semester we open a call. There you can apply for the large project. And then we also have user training, and this is one type of user training we are giving now by Anders Hast. We do outreach, software curation, and also dialogues with other infrastructure if we want to have some arrange some events, or like if we have some projects with others, like infrastructure, like more like in the development mode. And these were like, yeah, the Anders Hast, and also I was involved in the this user training from 2023 to until now. So these are like some examples. Like we have been to Umeå University, also here in Uppsala, and this the same HPC introduction to Python was given in April. So I think this is kind of like follow up, which is really nice that Jayant has invited us to present. And yeah, here you can just receive support. I can show you how you can actually mm, sorry for um, yeah. So here you can see my screen. If you go to infravis.se, here you have a button, apply for support. And this is a very simple form. You just write user support, your name, email ID, subject. Oh, sorry. I think I missed. I can just write this down. Something is a bit not working with my computer. Sorry for this disturbance. Yeah. And then you just write message here and then submit. So here you can apply for up to 100 hours support. And you can also see the projects here, like what kind of projects we have been working with. Like this has like more than 100 hours, or like in-depth support. And yeah, you can just scroll up and down, and yeah. And also like you can just access this if you want. And for like in-depth, we have this every year. So we just closed our last call. And yeah, so it was in October. Here we received like the large projects. Yeah, so I think that was all. I think I can just be done, because then Anders can have a little bit more time.
Yeah, thank you very much for introducing Infravis. And this is a lecture I partly have for Infravis and also the teaching at the university. Because visualization for me is not only about producing pictures, it's about the research process, really. Because from the visualizations, I learn a lot about the data that I'm working on. And I also learn a lot about the actual model or pipeline I'm using to do different kinds of classifications. So I hope this will be a good continuation for you now that have been studying a little bit about machine learning and how to do that in Python. So I have a lot to show. So I wanted to start with this machine learning example. If you ask people in the city 100 questions about their life and so on, then you get a 100-dimension feature vector that you can use for classification. And perhaps you can use it to tell, is the person Swedish or not? And then, of course, the question has to be related to that, such as, do they speak Swedish? Well, that's a good indicator that they might be Swedish. If they eat surströmming, they are probably very likely Swedish. But of course, there are also Swedish people who don't eat surströmming and so on. So that you have a lot of different indicators. And let's say that the blue dots here are Swedish and the red dots are non-Swedish. Well, then you can make the machine learning pipeline divide space like this, the green line, and this is called overfitting, when you really manage to separate the two classes perfectly. But if you go out and ask people in the city, some thousand more people, you will have persons that are not that are Swedish that end up around here, let's say. Because this person happens to like surströmming and speak Swedish, but is not born in Sweden. So the overfitting will destroy the results that you want to achieve. So the better classification is the black separating curve, because then you will have a better classification, but you will miss the sort of non-normal people that behave in an unexpected way. And why I'm showing this is because this happens in all data, more or less. You have outliers that you have to sort of live with. But also this shows that if you have high dimensional data and you can project it down to 2 dimensions, and if you get this kind of behavior, you can see that, okay, probably we can make a curve that splits the 2 data classes like this. If the red and blue dots would be totally mixed in a random way, then probably the machine learning would have a big difficulty in dividing them too. So dimensionality reduction, which I'm going to talk about now, can help you to realize how is the data behaving and how is the model that we have produced also behaving. So it's a really good tool for research. But we have to remember this simple fact that if we have a high dimensional object, in this case 3D, and project onto 2D, we see something which is not the truth. We see something which is an image of the truth, but distorted somehow. So we cannot trust it always, and we have to remember that. I'm going to show you, well, not this one, but the other ones, I will show you how they work in some detail. So perhaps you have been using principal component analysis, or PCA. And I had a hard time understanding what it actually does, but I got a help from computer graphics, since I work with computer graphics too. And if you have a computer graphics object like this dragon, and all the vertices are points in space, in 3D space, and you don't care about how the points are connected, but if you take all the points, do PCA on them, what do you get? Well, actually, you get 3 eigenvectors, and the first one is the most important one, which means the direction where the data changes the most. And then you have the second eigenvector, is the second most changing direction, and then the third one. So what you get is actually a perfect bounding box around the object. And this is useful in computer graphics when you want to detect collisions or compute ray tracing or something like that. But now we can project the points onto this axis and we get sort of a better description of the object. So PCA is very useful. And here you have an example where it works just fine. Perhaps you have seen this iris, Fisher iris data set. You just measure 4 measurements on the flower, the petal and the sepal. And if you look at each measurement in a parallel coordinate axis like this, where then each flower has, let's say, this width here, that there, and so on. So each flower sort of follows this line. You can see that now I have to like that. Okay. So you can see that the third and the fourth values seems to be the most descriptive ones. But if you have hundreds of dimensions, you don't know which one of them are the most descriptive. It's hard to search for them. So PCA, if you do PCA on this, the first axis will always be the most descriptive, and the second descriptive, and so on. So that helps you to find what is actually discriminative or descriptive in this case, which variables tell something. Like in the case of Swedish ones, you would probably have surströmming and language and those things coming in the first axis because it's very descriptive. It also means that the last axis, or some of them, are just kind of random or noisy. So you can use PCA for compression, remove some of them. And there are different algorithms to finding out how many are actually descriptive. So what you can do in all of the things I'm going to show you, you can actually do compression of the feature vectors first, remove some of the noise, and your algorithm will work much better. Or not much, but sometimes it will work better. So you keep that in mind and try if you have the possibility. So I will show you an example of MNIST. And MNIST has been called the hello world example for machine learning, because if your algorithm works on MNIST, it has a good chance of working on just about anything. So MNIST is just handwritten numbers, and you can see some are quite challenging to see. And if you take the image of each letter or number and just make a flattened feature vector of the whole image and run PCA on that, you get a scatter plot like this. So here you have the eigenvectors of principal components. And you see that, okay, there are some cluster here and some cluster here, but they are overlaid because it cannot project perfectly. But you see that something is going on here. If we then run TSNE, which is a dimensionality reduction technique, then we get this kind of behavior. You start to see very well-defined clusters with some points sort of ending up in the wrong place because they are written in a bad way. It can also be that the labels are mislabeled. That happens too. So you have strangeness in your data. And this method was invented by Geoffrey Hinton, who won the Nobel Prize last year for AI, and I think one of his PhD students, quite many years ago now, 2008. But when I saw TSNE the first time, I thought, wow, this is like magic, because I was used to PCA. So TSNE really helps, and it works in this way that it tries to find if 2 points are very close in high dimensional space, it tries to move them close also in 2D. And if they are far away in high dimensional space, it tries to separate them in 2D. So it's an iterative process where it moves around the points from some start guess, and then it ends up in this way. And the start guess is actually random. And if you look at the Python code, which will be provided to you, you see that there's a random start there. But you can also tell TSNE to use PCA as the first start guess. And that will probably speed up the process because the points are already close. It's just it has to separate them so that they are not overlapping. UMAP, on the other hand, is also a similar technique based on similar ideas, but works in a little bit different way. It's newer and it's also preferred by many. In most of the experiments I have done, TSNE works better for me. But I always tell people, try PCA, TSNE, and UMAP and see what you get and see what you can learn about your data or the model you are using. But UMAP tends to separate clusters better. They are more compact. And if one class is very dissimilar from the others, it tends to be moved away quite far away from the others. And that can sometimes be good, sometimes bad, because now you see the others more like a lump. So it depends on what you're doing. So I'm going to show you a little bit what I'm working with in 2 different projects. One is the City Faces project, where we look at who lived in Stockholm 150 years ago. So it's very much related to digital humanities. The other one is EB crime, where we look at age estimation in photographs, how old are people? And we also look at other things like DNA samples and so on. So it's a very interesting project. But first, I just want to tell you, how does face recognition work, since that's the data that also will be provided to you. So first, all the faces in an image is detected like this. So in this case, it's only me on the train. And then it's aligned, it's straightened up in case the head is tilting, it's straightened up and also cropped out, so you have the face. And from the face, you can then compute a face feature vector, which is just 512 usually, can be longer, can be shorter, elements. And usually you normalize it, so you can compute the cosine similarity. And that is simply the dot product between vectors. So the nice thing here is the pipeline for face recognition doesn't have to see my face beforehand to learn how my face looks like, because it knows how everybody's faces kind of behave. And then when it sees my face, it computes a feature vector depending on what it sees now. And if I have several photographs, it doesn't remember what it has seen. It just computes new feature vectors, and they will be hopefully very similar because it's the same face, but different angles and perhaps different time in my life. But it still will do a good job. We will see some examples of that. I used a pipeline called DeepFace in the early days of the project, almost 5 years ago. And I was very happy with that pipeline. It seems to work very well. And then, of course, since I like visualization, I thought, okay, I will visualize the feature vectors and see how they group into clusters. And then I got this kind of strange TSNE visualization. And since TSNE tend to make sort of a round cloud, this tail caught my attention immediately, and I thought, what is going on here? And then I zoomed in and looked at the tail. And since these are actually from the police registers, so they are kind of mug shots 150 years ago. So you have a front face image and you have a profile face image. And you can see here you have all the profile face images. And what does it mean? Well, they don't depend on which person they are. They are different persons, very close to each other. And this means that the pipeline failed to cluster in a good way, or failed to make a good feature vector, I should say. So the clustering isn't there. Instead, they are lumped together. So the profile face feature vectors look the same, even though they are different people. So this really helped me to understand that, oh, I have to change the pipeline. And when I did that, I got this much nicer behavior. It's the same data. And you can see you have small, nice clusters of the same person. And there's some distance between them. And here you can see how it looks like. Here we have one person, you have the profile face, you have front faces, and it's the same person. Here, the same person, or another person, but the same person in the same cluster. So this helps to prove that, okay, this pipeline works. It does what it was supposed to do. A little trick that you can use is to create a convex hull around the labels. Only if you know the labels, of course, or the identity of the people. So here the dots are quite large, so you don't see the convex hulls, but there's a convex hull around each cluster here, and this is a different data set, a modern one. But what are these lines? Well, it means that this point, for instance, is far away from its cluster, wherever it is. So what happened here? Well, it helped me to realize that, okay, perhaps it's a very difficult image. It can be a profile with mustache and hat and sunglasses and doing a very strange face or something like that, or very blurry. So sometimes the images are very hard and impossible to classify. But it can also be that the label is wrong. And that happens quite a lot. And always remember this, that there are lots of errors in data usually, even though it has been created. So this helps in seeing this. And by looking at this, you can sort of remove data that will just destroy your algorithm for learning if you do that. So here's another little bit example which was interesting. This is Selma Lagerlöf. I don't know if you know about her. She used to be on the 20-crown banknote, I think. And I took this image when she was younger, taken from a book. So it has been printed, and you can see this strange dots here from the printing process, the old printing process. So this image is hard because it has a lot of noise in it. And when I use this image to search for Selma Lagerlöf, I found all of these persons being similar to her according to the algorithm. And this is destroying everything. If I would use any of the other images, I would have just a few matches that would tell it's her. But you can see I set the threshold pretty high. Still, I get a lot of misclassifications, and I have one image of Selma there. So I made an algorithm that actually produces this result only. So it finds Selma and nothing but Selma using just that image. So that's nice. But how can we actually understand that this can work? How can it remove all of the noise here? Well, there is some inner consistency that I'm using. So here I take all the photographs of possible Selmas, and I send them to TSNE, and here you have all the Selmas. So they make a cluster, which is kind of far away from the others. But this person here is the closest neighbor. But it's not the closest neighbor in 2D space. So what is going on here? Why is this happening? Well, the reason is that the projection kind of fails, or whatever you would like to call it. I see it like it's not a 2D plane, but more like a cylinder. So this one is actually close to those ones. And this can often happen. So first I thought, okay, I just need to measure the distance in 2D space to know is it the same person or not. But sometimes the same person or a very similar person can end up far away. So remember the projection that we had before. I didn't have that image now, that the 2D space distance can actually lie to you. So be careful about that. Here I have another example from before, and this time it was TV who asked me, this woman here that is always around Putin, is it the same actor as they were thinking? And I really thought this is the same person because it's a blonde person, they have the same hairstyle, they really look the same. So I did an investigation and I found this interesting result. I could have just checked the cosine distance, but by visualizing, I could see, okay, those persons, they are kind of similar compared to others, but not really. And look what happens. I compute the distance between all of these faces, and these are from 3 of the images. So we go back. So these 3, and the cosine distance is 0.65, which is really high. But if you look at this person, the cosine distance between all of this image on average is 0.77, higher because it's from the same photo occasion. These are from different photo occasions. But when we compute the distance, or similarity, I should say, between those 2 groups, it becomes very, very low. And this is really far below the threshold to be the same person. So it's really different persons. And when TV showed this, BBC had a presentation about this the same day, actually, and they had the same results, so that was comforting. But they also knew the name of that person and the name of that person, so they were really two different persons. And I think she's like 10 years younger as well when you really look at the images. But the interesting thing is that this is a stewardess that were on some other photo occasion. She's dark-haired, she has a different hairstyle, she really looks different, but she's more similar to that person than those are similar to each other. And the distance is approximately the same in TSNE, but the similarity is quite different. So some face recognition software might think these are the same person, actually, but we see that they look so differently. But face recognition sees the geometry of the face rather than hairstyle and things like that. So please remember what this image shows, that closeness in what we see, like the Orion's belt, doesn't mean that the stars are very close in reality. It's a projection. So we have to think about that. I also looked at estimating, is it a man or a woman? And when looking at these three images, I saw one man and two women. But when projecting using TSNE, it turned out that this person ends up among the women. And this was also an interesting thing, that the women are here and the men are here. So that tells me that, oh, I can make a classifier just using the feature vector. I don't even have to train for, is it a man or a woman? It's in the feature vector, because men and women look differently, basically. So I thought, okay, this woman has been misclassified as a man. So I started to look in the Excel files we had from the police register. And it was Carl August Lundström. And his crime was ladies imitator, among other things. So it is really, or was really, a man. And this person called Carlotta ended up far way down here because one of the persons looking into this data thought that she looks like a man, and face recognition thinks she's a man. But of course, we cannot know because they are dead more than 100 years ago, all of these people. But as you can see, visualization helps us to understand the data better. And age estimation is a thing I'm working on as well. And this is from some paper. I just took that image and took the difference between them, and you can see sort of where is aging actually happening. And as humans, we guess around almost 5 years wrong all the time, up or down. That's quite a lot. While a good system can come close to 2.2 or something like that, but at least 3 years wrong. So even for a computer, it's really hard to do this thing. So I asked a master thesis student to train a neural network to see what happens. And it was around 5 years wrong or all the time, the so-called mean absolute error. And then I came up with the idea that you should try always, I suggest. I took the second last layer of the neural network. Just the last layer is for the decision that tells the age. But the second last layer is like a feature vector that tells something about this person. And I visualized, and I got this very surprising result. And this is TSNE. So the color here are the decision boundaries. A person in this area is 11 to 20 years old, and here they start to be 21 to 30 years old, and so on. So what is going on here? Well, obviously, people look the same when they are very young, and then they start to look the same when they are very old, almost 100 years old. But why are there two snakes here? Well, not surprisingly, but still kind of a revelation to me, is that here we have the men and here we have the women. So even if the system doesn't know who is a man or a woman. It only cares about the age. It still has to divide them somehow to be able to tell the age, because men and women look differently even if they are the same age. However, when they are babies or very young, we look very similar. Babies are round and cute, and it's hard to tell if it's a boy or a girl. And when we are very, very old, we start to look more similar again. But not always. And you can also see that there are some red dots here and some blue dots here. So why is that? I haven't checked exactly, but it's something I should do, because is it a very strange photograph? Is it sort of from the side? Is it a mislabeled person? Perhaps the red ones are men, or are they doing some strange face, or what is happening? So the visualization helps us to understand the pipeline, the model, what does the model do, but it also helps us to understand the data that we put in. And in this case, it's not the data for learning, but the classification that we have done. And here I used UMAP, but this time it's a different data. And you can see that the two snakes start from the same position, but they don't end up in the same position, which was kind of interesting. They also have something there, which I haven't checked yet. But the first thing that struck me is that the snakes are kind of entangled. There's an overlap here. And my first thought was, okay, people in this age look the same. But when I run this same data on TSNE, it didn't overlap. So what is happening? Well, here's a case where UMAP cannot or do not succeed in sort of, how to say, unwrap the plane into a perfect 2D plane. So it's the plane is kind of distorted, and the snakes are just visually looking as if they are close, but they are not. So it's just an illusion. So please think about this. Try UMAP, try TSNE, try PCA. What happens? Because if they are close in one projection, they might not be close in the other projection. So we cannot draw very good conclusions always about closeness. So here it's just an illusion that they are close. And once again, it's men and women, of course. So this sort of a similar thing happened when using UMAP, but it's the same pipeline. So you can see you have a little bit of red dots in the blue area, and perhaps vice versa, but very few, it seems like. So a researcher that has been presenting in our courses in Uppsala, Alexandro Telea, he made a paper about different dimensionality reduction techniques. And you can see there are lots of them. I have only talked about UMAP, TSNE, and PCA is here in a little bit different variants. So please think about this, that UMAP is perhaps one of the best ones, but TSNE is very close. And in the paper, they have something strange that I haven't really understood. But I remember Alexandro Telea talking about that TSNE in many cases were better. And for me, it has usually been better. But for you, it might not be the case. So try all of them. And that's sort of my suggestions here, that try both of them. Try PCA as initial guess. If that's possible, it will be kind of faster. And if you have any questions about dimensionality reduction, please feel free to contact me, and I will try to explain as much as I can. And I almost forgot something. Yes, if you want to run this, what I did was to create this kind of environment. I don't know exactly what you have been teaching in the course, but for me, this worked very well to set some Python version. And the only thing I had to install extra was UMAP. TSNE is in something called sklearn, I think it's called, for machine learning. And then just activate it and use it. I use a notebook all the time because it's sort of easier. So that was my presentation. Thank you very much for listening.
Thank you, Anders. I can just point out that this particular exercise that Anders was talking about is available in the exercise folder. It's in the folder called Dimensionality Reduction. And you can find the data set as well as an IPython notebook there that you can run.
Yes, thank you. And I have actually updated this quite a lot since I created that one, but I didn't send it because I want you students to look at the old exercise and think, how could you use Plotly instead and make everything interactive, and how can you improve it? And let's see, I have actually examples from using this here. So I think you, Giant, will put this up so the students, and just click on these links and you will have examples how to use TSNE, PCA, and UMAP.
Yeah, thanks, Anders. I'll do that.
There's a question also in the chat.
Oh, okay.
Did TSNE and UMAP both work on image data or only features?
They work on anything kind of. So you can have image data. Both of them works for that too, if it's good data, so to speak. So if TSNE can make clusters, UMAP can make clusters, and vice versa, but they will look a little bit differently. So you can see image data as a feature, but what I didn't show today is that you shouldn't really flatten an image and use it like that. You should try to extract a feature from it, and that's what convolutional neural networks do. But you can also use handcrafted features like histogram-oriented gradients or something like that. So then you can see how the clusters will start to behave better, and you get better separation. So you can actually investigate how well your feature extractor works in this way. Yeah. Any more questions?
So flatten the reduced layer in a CNN question mark.
Oh, yeah. So I guess what you mean is that I took out the. Yes, exactly. As I understand, the second last layer in the model, the weights there, what it has, you can make a feature out of that. And to be honest, I didn't know how to do that, so I asked ChatGPT, and I got code that worked. So I was very happy for that. So I could use it on the model that my master thesis student sent me. Yeah, so I will certainly do this more myself because it really helps understanding. So if you read blogs and stuff, they talk about embeddings in latent space and things like that. So that's what they mean. So
Yeah. Okay,
I'm
then.
done, unless there are some more questions.
Pedro is asking a question.
Yes, that I see that question. I got that question. I actually had a presentation this morning, the very same question. And I don't know, but I think you can do it. I mean, you can, for each time step, if you have a feature, you can visualize them. And if you only have like a singular value for each time step, I guess you can treat the whole time series for each data point as a feature vector and see how it changes over time. I never tried that, but I think you will get an interesting visualization doing that. So if you ever try, please show me. I would like to see how it works. But if it just is messy and noisy, then you understand that, okay, this was hard. But I think you will probably, if there are some tendencies in your data. You will see that in the TSNE visualization. They will start clustering. Thanks, Pedro.
All right, then with that, thank you, Anders, once again. And thank you, Nikita. I think she's left. For this, your experiences with different dimensionality reduction techniques.